Welcome to chapter 20. We have now seen in chapters 18 and 19 quite a bit on the design and analysis of weighting. Of course, when it comes to a real data set, a big one like the Belgian Health Interview Survey with a relatively complex design, a number of these features are coming together, and I mean a number of design features come together into the weights, because recall that weighting is introduced for a variety of reasons to correct for the differential selection probabilities between regions, one. Second, to correct for the differential selection probabilities of individuals within households, two. And these are really the most important contributions to the weights. But also, corrections can be done for a number of other variables, like, for example, provinces. And even though provinces were sampled proportional to their population size, the actual sample fraction, the fraction of, or the percentage of people from a certain province in the sample is not necessarily the same, and actually isn't the same, of what it is in the population, although the differences may be slight. So we can correct for such phenomena as well. As before, we will concentrate on logarithm of body mass index, logarithm of VUC score, general well-being, general health questionnaire with 12 questions, and stable GP. Now, the program to be used, for example, in SAS with survey means is such where you include the weight statement right now. We had the cluster statement, for example, before, or the strata statement before. Now we use the weight statement. Recall that domain is making sure that apart from a Belgian result, we get a result from each of the regions separately. So what we see here is the data, pretty self-explanatory like always. So for example, the fraction having a stable GP is 93%. That's what we get here. What we see at the top is still the same number of observations that we had before several times, and the sum of the weights. Now, the sum of the weights as such is not relevant for a survey procedure. In other words, you multiply all the weights by 10 and nothing will happen because it will automatically calibrate, because the weights come into the numerator and the denominator. And yes, selection probabilities, they should sum to 1 somehow, otherwise they're not probabilities. But weights are the inverse selection probabilities. As long as I multiply all of them with a factor, or I don't, I rescale, in other words, nothing will really happen. It's like going from meters to kilometers. I still represent the same distance, yet in other units. Okay, and the 93%, the 0.93, is exactly the number that we had studied before. And then also, do we get the same numbers split over each one of the regions separately? Okay, so if we, for example, with your permission, go straight to stable GP on page 593, what we see is that the 90% we had all the time before now has become 93%. And that's because we now properly take into account that Belgium is made up of a 60%, 10%, 30% mixed over Flanders, Brussels, Wallonia, respectively, rather than 1/3, 1/3, 1/3, which is what the sample would tell us naively. If I switch back to body mass index, you see that the standard error has changed. For example, in simple random sampling, the standard error was 1845, and I'm forgetting the decimal sign here. It's now 26.51. Well, that's 50% higher. That's literally the price to pay for weighting. Weights introduce additional variability. In different terms, you select unbiasedness, or you get unbiasedness, or you pay for unbiasedness with a currency called efficiency loss, increased variability. It's not necessarily 50%. I didn't say it's always 50%. I didn't even say it's always 50% in the Belgian Health Interview Survey. Like, for example, for the VUC score, it goes from 89.54, so 90, say, to 132. It's a different magnitude by which we see things vary. Okay. For stable GP, we go from 32 to 35, which is a much more modest correction. So, inferring that the impact of weight is an increase of variance with 50%, I don't dare to say that in a specific study. It really depends on the variable you are studying, the subgroup or the domain you are studying it for, etc. Okay. In spite of that, I say roughly a factor 1.5. I think it's almost fairer to say you increase by at most a factor 1.5 among the variables we have studied here. I don't dare to say that this is true for each and every item and variable you will get from the Belgian Health Interview Survey. So, maybe superfluous, but let me state again, if you do an unweighted analysis, you say that Belgium is roughly, and these are rough figures only, is made up of 1/3 of each one of the regions. If you do that in a weighted fashion, you take the Brussels estimate for 10%, the Flemish estimate for 60%, and the Walloon estimate for 30%. For log body mass index, it so happens to make no difference. Well, a very small difference. And that's because in this case, there is not really a lot of variability from region to region. So the regional effect here is very minor. If you do that for the VUC score, there you find that in Flanders, the VUC score is 1.5, lower than for the other two regions. But that's also the largest region. So if you weigh that properly, the lower number will be more important, and that, of course, brings the estimate down. Okay. So for GHQ, it's very similar. For stable GP, there the variance didn't change very much, but the point estimate does. It does change quite considerably. Okay, good. Now, what I just did is I used survey means because I wanted to calculate a simple means. Likewise, I can use survey reg instead, and likewise does that procedure allow for weights into the analysis. You get your estimate of your regression coefficient, which in this case is nothing but the average log BMI before. You can even do that in proc mixed, where you use the weight. And again, you get the same estimate as we found before. All right. So, if we look at the overview now, what we see, for example, is simple random sampling produces one figure, 3.1872, which is carried over to stratification and to clustering. No wonder they typically do not change the point estimate. They have an impact on the precision, though. For weighting, for the first time did I see the point estimate change. Whether I do that with survey means or with survey reg or with mixed, it's the same number. Correction, it's about the same number. 3.1853 or 54, that's the same. But there is something bizarre happening with the standard there. If I use the linear mixed model that we saw before, I get the impression that the standard there is quite a bit smaller. Well, why is that the case? And even previewing a little bit what's below here, if I combine all of them, also there, do you see a difference between survey means and mixed? To be very specific, that should not happen. This should not happen. Something seems to be a little wrong. We need to think about that for a moment. We need to keep that question on the shelf. We want to resolve it. Okay, for stable GP now. Well, stable GP is 0, 1. So rather than using survey means, which we did, and that's actually fine. We can leave it at that. But just for illustration, and because we want to go forward, so maybe you should think a little bit like, why are we doing this? If we can estimate stable GP in a proper weighted-based fashion, why on earth do we need additional procedures? That's a good question, and also about that we need to think for a while. We can use, for example, the survey logistic procedure, which is, of course, a survey procedure as we know, and we can use some general purpose procedures like GenMod for GEE, generalized estimating equations, which we studied before, GLIMIX and NL mixed for the generalized linear mixed model that we studied before. Okay, survey logistic, if we use that, it's about the same code, roughly about, as we used before for survey means, but we now find the intercept, so-called intercept of minus 2.62. Oh yes, that's because here we're not estimating a probability, we're actually estimating the logit of a probability. GenMod, switching to GEE, with also here the weight included, and you see, for example, also class HH, because that's our subject. Incidentally, we find the same intercept as we did found there. Okay, with recall, an empirical standard error, which is the properly corrected standard error, and then here our penny drops, a model-based standard error, which is 0.0015. Now, the 0.06, believe me at this time, is much more realistic than the 0.0015. What's the reason? Well, with weights, we have to be very careful. Here, there is a bifurcation, a split, a Y fork, or a T-junction, if you want, between, on the one hand, special purpose survey procedures, like survey means and survey logistic, and general purpose procedures that allow us to use a weight too. First, survey procedures. They know that weights are survey weights. So as I said, you multiply them by 10 and it will recalibrate, no harm done. So you take your weights, you multiply them by 10 or by 17.32 if you like that number. The result in the output will not change. It will, in every minutious detail, it will be exactly the same. If you go, though, for general purpose procedure like GE, and by that I mean you can apply GE pretty much out of the context of surveys, you will actually use the weighting procedure in a different way. Most of the weights are intended to have multiplication or multiplicity, I should say. For example, a weight 10 in a classical procedure means that that particular realization, that particular outcome is realized for 10 people. So it should count as 10 people, and therefore it counts towards the sample size and the variance gets smaller. And that's what we see happen here, because the sum of the weights is so tremendously large, the standard error is way too small. What's the solution? You have to calibrate the weights yourself in this case. Okay, so if you do the same with proc GLIMIX, you may also have to standardize the weights because it's a general procedure as well. Okay. Other than that, it's the same procedure we saw before, where we now include the weighting indeed. Okay, same story. If you do the without empirical, so the purely model-based standard error or the naive standard error, you get a standard error that is way too small and actually comparable to what we have before relative to if you do that with the empirical standard error. Okay, so here again we have quite a bit of overview in our procedure. On this slide here, 607, we even don't see anything that we haven't discussed before. Weighting is only on the next page, 608. And again, you see your numbers 2.6290, etc., that we saw several times before as the logit beta or minus the logit minus beta. Pi is the corresponding probability, and whether you use survey means, survey logistic, GenMod, or GLIMIX, you get about the same results. And here the standard errors are fairly similar. 35, 35, 40, 35. But 40 is different. Yeah, but not much. That's the price you pay for using a non-likelihood-based method like GEE. The fact that you basically allow the correlation to be misspecified, you pay the price for that here at this time. Okay. Good. So if properly done, the weighted analyses give a very similar result indeed. And the bottom line, the conclusion is it's not so very difficult to do. That not only concludes chapter 20, it also concludes part Roman 8, and in the next part we will look not at any new material, but rather an integrated analysis of the Belgian Health Interview Survey.